this inside is going to end up being negative q, right? Spread around this side right here, right? Now, I don't know what's on the outside because it depends whether this is bigger or this is bigger, right? Whichever one's bigger is going to win. And that's what's going to be distributed on the outside. But I don't know what that is. Like, if there's no charge on this one, there'd still be negative q down here. There'd be positive q on the outside, right? So inside this realm, the charge enclosed is plus q. The moment I hit the metal barrier, though, there has to be no electric field because charge is going to continue to move until it cancels out the plus q. The way it does that is by having minus q on the inside. Right? Because as long as there's charge exposed here, electrons are going to continue to fall down because it's a conductor. Right? The moment it's complete, these charges are equal, that means my charge enclosed is 0. Therefore, there can no longer be an electric field here. Okay. There's no electric field, there's no force, so there's no reason for a charge to move.
But then, so when it gets past C,
then the things get interesting. Now, there's two ways to look at it. One of them is to try to figure out what charge is on the outside, and that would be the difference between the two, right? Mm-hmm. Another way I look at it is, look, the charge enclosed is just plus q minus q. Why? I don't really want to know where it's arranged. I'm not even going to look at where it's arranged. As long as it's symmetric, I don't care. Right? Okay? All right. Got it? Got it? All right. Voltage time, probably. Yep. Voltage time. Voltage time. I recommend you start with C first. I recommend you start with C first. No. Yeah, so I recommend you start with the last one. I recommend you start with the last one. So for C is greater than R, how are you going to find the voltage? The electric field is going to be based on this, correct? So I'm going to go the integral from infinity to R of this equation here, which is Q minus Q over 4 pi R squared E naught dr. That's a R to the negative 2. Can I what?
Can you take out your Q minus?
Yeah, I can take out everything. All that's garbage. E naught, and then R to the negative 1. And now I got a problem on my hands that I'm going to have to think about really hard. But we'll do that in just a moment. From infinity to R, we know that infinity is going to be 0, so I'll have to worry about the first one, which is going to give me Q minus Q over 4 pi E naught R. Agreed? Okay. So why am I saying minus that's a problem? Because we have to think about it really hard. Usually what we do is we say, look, I'm gaining potential as I get closer to the sphere, right? But unfortunately, is this positive or negative? It depends on the magnitude of the charges, doesn't it? So now look at this and go, well, look, if Q is a negative 1, right? If Q is bigger, then this whole thing's going to be negative, which means I'll have lost potential coming down from infinity. A positive charge would do that. If Q is positive, if this is bigger, then this whole thing's going to be positive. The positive charge is bigger, then I'm going to have a positive here, in which case it should increase my thing, right? So that negative needs to disappear, okay? And again, you can disappear it by putting in the original equation, right? The integral, you're allowed to put a minus there. In fact, it's on the formula sheet that way. Or you can simply say it needs to be positive when I'm done. That's got to be my voltage. Cancel out an R?
So we're just making the assumption that the positive charge is larger?
No. If it's not larger, then this whole thing, move your head, Fleming.
What?
This whole charge would be negative, right? This whole thing would be negative, right? And it would be negative. So it works out for me either way. But I did have to pause and think about it. Like, you have to get your brain on and go, wait a second. But I don't know which one's bigger. I can't use my old, it has to be positive towards positive, or it has to be negative towards negative. I don't have that option because this problem doesn't tell me whether the whole thing's positive or negative. Turns out, though, if I just look at this and go, I can still figure it out from that. Again, if you put a negative at the beginning, your negatives would cancel out. That would also do the job. Okay? What is it between B and C? No, it would not be 0. Because we're asking for a potential at a point between B and C. What would it be? I still got to come in from infinity, don't I? And all the way from infinity until I get to where I do have electric field.
Until you get to the edge of this.
Under the outside sphere, which is what? C. So the voltage anywhere inside of the outer shell is going to be Q minus Q over 4 pi E naught C. Right?
Yeah.
Because that's what it's going to be when I get to the outside shell. And then after that, it doesn't matter because moving around inside, the electric field is the same. I'm not gaining voltage or losing voltage by wandering around where the electric field is 0. Yeah? All right. So that's the next one, B and C. Now we got to go from A to B. Now, between them, what do I do? Now I'm going to use this electric field, aren't I? So I'm going to do this to get to the outside, plus the difference between those two, right? So I'm going to have to go the electric field. So the voltage is going to be equal to the voltage to the outside, right? I'm ignoring doing the voltage on the inside, right? So this is going to be this. Q over 4 pi E naught R to the negative 2 dr, right? Using that electric field we found earlier. So that's going to be Q over 4 pi E naught R. The inside is positive or negative, did we know? I need to check that. It's positive Q, so that's plus Q. So it's got to increase, so I need a positive number when I'm done. I'm happy with this. Okay. Now I'm going from where to where? Maybe I'm not happy with this. I better double check that too. I'm going from B to A, aren't I? B to A. So my voltage would be this plus whatever this is going to end up being, right? Okay, so now I'm going to look at this very carefully, and I'm going to be unhappy with it because I wasn't careful. Q over 4 pi E naught R, or R is going to be A, minus Q over 4 pi E naught B. Now, who wants that one? Who's going to tell me whether my signs are right or wrong? Never said. Tell me the signs are right or wrong.
I got a feeling they're wrong.
All right, why?
Because
I should have minus sign in front of my voltage equation? Yes.
yes.
Or use a physics reason. The physics reason is this. I look at this and go, look, B is bigger than A, right?
Yeah.
So this is going to be bigger than this one. This is going to be smaller than this one. You said, right away. Am I right? Wait a second. I'm dividing by a smaller number, dividing by a bigger number. Right? So this whole thing is going to be bigger than this one, agreed? Because A is a smaller number than B.
Yeah.
So that being the case, this is going to be positive. I want it to be positive, so I'm wrong. It doesn't change its sign. It's good the way it is. Okay? And I need to add on this piece right here. Plus Q minus Q over 4 pi E naught C. Oh, this is wrong, though. What is wrong? This is wrong. Why is this wrong? No. We're not going from B to A. We're going from B to... No. We're going B to R. The arbitrary distance in the middle. Right? So that should be an R. Now the last part. What happens when you get in the sphere?
Wait, the last question.
Mm-hmm.
So when you just take the total that you've been using and then add it on to what you
Even if you that instead of R, it's A.
That's an A.
Yeah.
That's it. Right. Because you would have to then go from B to A, so you'd lose that much voltage going from B to A.
Why when you pass the inside of the shell, doesn't the voltage change?
While you're on the inside of the outer shell?
Or, so when you get to the inside of the outer shell, wouldn't the inside of that also be charged and then exerting voltage on?
Right, but inside, what's the electric field between the 2 points?
0.
0. So there's no preference between any part of that thing, right? So from here to here, there's no difference in terms of voltage, right? I'm not going up or downhill. I can move a charge around, and here it doesn't. It's not affected by the fact that because there's no electric field there, right? Hopefully it's already set up so that the charges are where they have to be, make the electric field there. Make sense?
If there wasn't a conducting sphere, would we have to do all this?
If it wasn't a conducting sphere, you might have a charge distribution, which means you'd actually have to integrate during that middle section. You actually have to do it, right? Because it would be losing or gaining voltage that went through that outer shell, right? But because it's a conductor, we don't care. It's going to be, there's no effect there. All right, find the potential difference between A and C, between R equals A and R equals 0.5A, find the charge per unit area on the inner surface of the outer shell, and find the total induced charge on the outside of the metal shell. Bam! More good problems for you to play with. So between R equals A and R equals C, you just have to worry about the middle range, so you just do the middle section. For this, from R equals A to R equals 0.5A, you would end up with 0 electric field because there's no electric field inside of the conductor, and therefore there would be no voltage change. Yeah. Yes. All right, find the charge per unit area on the inner surface of the outer shell. I'm going to make Reith do this one. See if he's got it. See if he's got it. I think he's got it now.
All right. On the inside of the shell. Do we have to use a Gauss?
Not at all.
Okay. Alright,
How do I figure out my charge per unit area on the inside of the sphere is?
you just take the charge that's like on that and then divide by the length.
The charge is on what?
The inner part of the shell.
Well, yes, but what's the charge of the inner part of the shell?
That's where my problem is.
Ah.
It's got to balance out with Q if it's greater.
So it would be what would be the total charge distributed on the inside of this to balance out that positive Q?
Negative Q,
Negative big Q, little q.
big Q.
Negative big Q. So it'd be negative big Q over 4 pi R squared. R squared in this case would be B squared. So that'd be our charge per unit area on the inside.
That's the charge per unit area?
Yep, because that's the area that inside of the sphere, right?
Okay.
And the charge you just told me has to be negative Q to cancel it out. I'm with you. That is the correct answer.
Is that like adding inside the outside? No idea.
So what's the charge and the induced outer edge? Induced, that means that it's that because they have a charge on the inside, it's messing with the charge on the outside, right?
Wouldn't it be like little Q minus big Q?
It would be, I would go big Q minus, no, I wouldn't. Okay, on the outside, hold on, let me double think this. Yeah, it would be Q minus Q.
So that's just 2 magnets.
Right? It could either be the negative Q wins, in which case that's what's left over on the outside. After it's dumped a bunch of negative big Q to get fix that.
We're done with the packet now.
We're done with the packet now. We're done with the packet now.